And today we are very happy to have Professor Radu Roiban from Penn State University telling us about supertranslations from scattering amplitudes.
Thank you very much. Thank you very much for the invitation. It's great to be back here. I should one tiny comment to my title. This S, we may debate whether it should be plural or singular at the end of it, but at least the super translation part is. So this talk is based on work with Asad Al-Khidir and Donald O'Connell, and it draws quite a bit on slightly earlier work done with Donato Bini, Thibaut Damour, and Stefano De Angelis, Andrea Giralico, Aidan Herdershi, and Fei Tang. So infinity is a complicated spot, and it's not actually a spot, it's a manifold, and it's complicated, especially in gravitational theories. And there it exhibits symmetries, asymptotic symmetries that they're usually referred to. So the version 0 of the plan for this talk is to explore these asymptotic symmetries and their effects on observables using on-shell methods. And we're going to focus on the gravitational field and extract observables from it. So having said all of this, somebody in the audience might already object having gravity and observables on the same slide, if not on the same sentence, because there are no local observables in general relativity. So what am I talking about? I think I'm talking about the next best thing, which, depending on the specifics of the context, one can have in asymptotically Minkowski spacetime, one can construct differential cross-sections or a proxy to that, the S matrix, which are sort of local. They're local at infinity in some sense. Asymptotically anti-de Sitter space, one also has sort of local observables, which are, they're not local in the bulk, they're local on the boundary. They're the boundary coordinates. And one could also have final state expectation values, which are again local in some sense. And this is all of these have desirable features. In particular, they are invariant at least under small gauge transformations. And they are mostly infrared state.
So, in quantum field theories, then you have graviton running in the loops, but not as external state. Still talk about observable asymmetric elements in that case?
Yeah, I think so.
It's only you're concerned about external gravitons, then you're doing what you're saying. Okay. Okay.
So since you mentioned gravitational field, there it is. So an important observable related to of this type has to do with it's actually the gravitational wave at the gravitational field at infinity. So I was talking here about asymptotically Minkowski. This asymptotic gravitational field at infinity is a wave that that oscillates on top of Minkowski space, and it dies out as 1 over r as one goes to large R. So strictly speaking, at R strict infinity, there is nothing there. So this, what I'm showing you here is one bit of the gravitational field that drops off like 1 over R. And this is sourced by a scattering process that happens at the origin in space, in space-time. And it's, just to be definite, it's the part of the it's the off-diagonal bit of the transverse traceless part of the gravitational field, which has to do with messing up the angles between 2 directions. What you see here as colors is the departure from the right angle. Green is right angle, and then blue and red are less than 90 degrees and more.
How should I interpret the gravitational wave you observe in the laboratory?
That's exactly what you're going to observe in the laboratory. You pick a point here. This is the celestial sphere. LIGO, for example, sits.
But we are not in asymptotics, right? We're in the lab. So in what sense that's asymptotic?
This is asymptotic in the sense that the event happens 20 light years away, and 20 light years is pretty darn big. But yes, now we can have a very long debate about exactly what asymptotics means. Now at LHC, for example, asymptotics is this far. And everything works fine. 20 light years, I think we are pretty safe.
Okay.
All right. Anyhow, so what you see here in the beginning, there's a long period of green where nothing happens. This is before the gravitational wave hits us. And then what you see at the end, colorful and stationary, that's the gravitational wave now. All right, so let's spend a little bit of time talking about how we actually compute this stuff. So how do we compute this thing? From a general relativity point of view, if one has the metric, one just subtracts, it multiplies by x and takes the limit. But how do we actually compute this stuff? One starts with the operator that one has to compute this expectation value of. And because we're interested in the gravitational field far away, we can talk about linearized gravity. So this is how it looks. A and A dagger are the usual creation and annihilation operators. Epsilon are the polarization vectors, and standard. In this form, it certainly doesn't take into account the fact that we are very far away. So we need to do something about that. And there is a little calculation. Don't worry about the details. This is still slide number 3, and I was told I shouldn't have complicated equations on slide number 3. Anyway, the idea is that there are some operations that are being done to this, and and those operations enforce the large distance limit. And because of that limit, one can do a saddle point approximation and carry out most of the integrals except the one over the frequency. And then one is left with this. So there is a wave here, frequency. This is the retarded time. The polarization doesn't change. The creation operator is the same. The only thing that happened was we basically integrated out angular direction. This saddle point approximation makes one assumption on top of large distance. It also makes the assumption that the frequency of the wave times the distance is much larger than 1. This is a great assumption. If x is 20 light years, this is most of the time all right, except in one instance. Can anybody point to under what circumstances, if x is extremely large but finite, this is violated? Small. Omega is extremely small. For example, omega equals 0. What is the...
Because you could handle that. That's why we didn't say it.
That's the purpose of the talk, so to show you how to handle it. So omega equals 0 is, it's a very special point in momentum space, but it's also something that we understand very well. We live in a space that corresponds to omega equals 0. It's time independent. Omega equals 0 means that the space is flat. So these are, on the one hand, zero energy gravitons. On the other, they represent spacetimes that don't change. So in such spacetime, or modes of such gravitons that correspond to spacetimes that don't change, are difficult to deal with via this. So the message is that we should keep an eye on these guys and see what their purpose in life is. Is their purpose to make our life miserable, or is their purpose to teach us something? All right, so that's observation number 1. Observation number 2 is that gravitational wave at infinity, as long as it's a fluctuation on top of Minkowski, while it may be invariant under gauge transformations that drop off fast enough, in particular faster than 1 over r squared, they are not invariant under diffeomorphisms that don't do that, that fall off as 1 over r themselves. These are so-called large diffeomorphisms, and in asymptotically Minkowski spacetimes, they represent BMS transformations. So for probably the very few of you who don't know about BMS transformations, let me say a couple of words about them, and I'm happy to be corrected, assuming that I say something completely stupid. So they are usually discussed in the so-called boundary gauge, which is a bunch of zeros for the metric coefficients, and a particular fall-off for the remaining ones. And the main character of our talk will be this CAB, also known as the shear tensor, which is the transverse traceless part of the metric, basically. So it encodes the gravitational wave that is the one on the previous animation. Another bit that will be interesting for us will be this M, the Bondi mass, which will make an appearance only at the end of the talk. So the transformations that the BMS transformations are those transformations which preserve this form of the metric and also this particular fall of the metric coefficients. And one of them, the so-called supertranslations, basically shift the retarded time by an amount that differs, that depends on the angle. Right? So we can shift by some amount in this direction, some amount in that. Under such a transformation, the shear tensor changes by this by this much. So n is the so-called New's tensor, the derivative of the shear with respect to u. And then there is also one can think of this as the transport term, if you wish. And this is an inhomogeneous term that in principle allows one to set part of the shear to zero. There's another charge corresponding to this transformation, which is given by the bonding. So where do we go this time? Okay, so this said, all observables that depend, I should say, this red term, brown term here is time independent. So it is in fact corresponds to a zero frequency mode of the gravity. So from here, it sounds like there should be a connection between these guys that potentially cause trouble here and this kind of transformation. And who should be sensitive to this is basically anybody, any possible observable that depends on the undifferentiated shear, because this part will be preserved. If the shear is differentiated specifically with respect to the retarded time, then this term is going to go away. Nobody knows about it. We're all going. Okay, so the plan will be to focus on this kind of transformation. And of course, the gravitational field itself, h mu, is one of them. All right, so having said all this, a better version of the plan is this one. So we are going to explore the connections between various manifestations of zero frequency modes using field theory methods. And to that end, I'm going to first review a little bit the observable base formalism for computing observables in gravitational theories and also in other theories. This is the idea of computing observables as expectation values in the final state. We are going to see a couple of examples, what happens at order g squared and at order g cubed for the gravitational field. Then we're going to try to resum these zero energy modes and see where they lead us, and then talk about another observable that's known to depend on the undifferentiated shear, the field angular momentum. And then at the end, we're going to make a connection between what we are deriving with field theory methods and the Noether charge of supertranslations from a GR point of view. All right, I should have said, please feel free to interrupt and ask questions at any time. Okay. All right, so are there any questions about the motivation?
What is the intuition for zero frequency field?
Well, the intuition is that on the one hand, they need to be kept track of because of this.
Time independent configurations. Does it have really observationally? Is it?
Yeah, so I skipped about this bottom of the slide, but here is an instance where we actually see it with the naked eye. Right, start with 2-point particle. For the sake of the argument, take two Schwarzschild black holes, which are mostly static.
Okay.
Now let them scatter off each other and look at in the far future. Right? They will scatter off each other. They will be at different positions that they originally were. Right. So the space is again essentially static because energy is conserved, but they're located at different points. So there is certainly a big part of the difference between these two spacetimes is time independent. Right? One is particles here, the other one is particles there. So one can see this zero energy modes.
Observations of colliding black holes, does it play a role, such an entity?
We're going to see in a second.
Okay.
The waveform basically looks different. It differs by some time dependent thing.
So you say, but what do experimentalists say?
This is a debate to be had over a beer.
Okay.
Sorry.
So are you considering omega 0 or omega's arbitrarily small? Because it looks like they're kind of quite different if you actually plug in omega 0.
Omega strictly equals 0 is a lot more special than omega tiny but non-zero. So we're going to focus on omega strictly equals 0.
Okay.
There will be a little bit of regularization, but the regularization will be such that these omega equals 0 modes will be given some tiny energy, but they will still be unmixed with the modes that belong to a continuum. Okay. So just to get back, I didn't mean to be rude. It was whether these are observables or not. It depends on This is more of a philosophical problem in the sense that with our current technology, the answer is no. With, depending how far in the future you want to think about, if we could have a LIGO on Earth and one on the other side of the galaxy, then they could, and the two could communicate and be synchronized. Then one could detect the zero energy modes from the time dependence of the outgoing waveform. So, all right, where were we? Right here. Okay, so before getting to the observable base formulas, we still want to compute classical things based on shell methods, so basically quantum things. So we need to learn how to take the classical limit. Everybody here had field theory. Let's see, who believes that everything classical is at 3 level? Okay.
Very alluring proposition.
So the answer, well, not everything that is classical is at 3 level. And the idea is that there are at least 2 distinct classical limits that one can take. One is the one that says that everything classical is at 3 level, and that's a perfectly valid limit. But there's another one which is in the sense of the correspondence principle. So in the sense of the correspondence principle, classical physics comes out of quantum theory as one takes charge is large. Okay, so here we want to scatter things that we want to associate to planets or black holes, as the case may be. These are large things, they're not electrons. So we need to make sure that the fact that masses are large and their momenta are large is actually encoded in that limit. So one way to encode that is to declare that the de Broglie wavelength of the scattered things is much smaller than the distance between them. Awesome. So with that in mind, it turns out that this is equivalent to saying that the angular momentum of the relative motion of the two is much larger than 1. It's a conserved charge that's large. And it also says that the momenta of all these big particles the momenta are a lot larger than the momentum that's being lost by each of these particles. So this, in retrospect, this makes sense. If the momentum that's lost by one of these, by Earth going around the sun, if the momentum lost by Earth going around the sun at any one point is large, then it will go this way. It doesn't go very smoothly. So just, intuitively, this is reasonable. So if we mix this with the idea that Newtonian potential is classical, one figures out that the scattering amplitude, say 2 to 2, 2 matter particles goes to 2 matter particles, has to have this kind of dependence on the momentum that's being lost by each particle. Q is the momentum that's transferred in between. And similarly, the same is true about basically any potential that might describe it. Now, a little bit more thought is that as one loses gravitons in such a scattering process, nothing should really change. Basically because on the one hand, we know that Bremsstrahlung happens all the time in classical physics. There is no suppression. And on the other, the momenta lost in such gravitons, they cannot be large because again, if one lost large momenta at any one Bremsstrahlung effect, then again, Earth would do this. What do we infer out of this relation is one, that not everything is 3 level. Here we are talking about, say, 2 to 2 with no additional gravitons. And yet we are writing here an arbitrary function of G, Newton's constant. If this were just 3 level, G, the power of G would be fixed to be, I guess, 1. And that would be the end of it. So the point is that loop effects are, in fact, pieces of loop effects contain classical information. And it's part of loop diagrams or loop amplitudes that have this particular dependence on the momentum. All right. Questions? All right, so an example of this is a 3-level example, but all the same. So Newton's potential coming out of a scattering amplitude calculation. This is the scattering the 2 to 2 scattering amplitude. Q is again the momentum transfer. And if you Fourier transform this, you get that. Newton's potential with relativistic corrections. There are higher orders in Q here, but they are quantum mechanical in this sense. And you've encountered them not in the gravitational context, but in a QED context under the name of Darwin terms in your study of, say, the hydrogen atoms. All right. So now back to the observable wave formalism. So the idea is that an observable, any observable, for which we can associate some operator, is constructed as the difference of its expectation value in the final state minus its expectation value in the initial state. So this just says that it will change in that observable. And the outgoing state is the evolution of the incoming state with the S matrix, with the E to IHT, the most intensive. So there are many such measurement functions, O, that one can define. We're going to focus on the gravitational field, which we just discussed a little earlier. And taking this guy and plugging it in here produces two kinds of terms. One with a single transfer matrix T and one with two transfer matrices. And if one assumes that there are no gravitons in the initial state, then some of these terms drop out. And one finds these two terms. And this is, again, in frequency space. To find it in the time domain, one still has to Fourier transform with respect to the retarded time. But that's perhaps that's a separate story. All right. So what do each of these mean? So the anatomy of this object. In going from the previous slide to this one, I let this A act on the initial state here to produce an incoming graviton. And here I am inserting a complete set of states on either side of A, so that I know how to compute each of these in terms of S matrix elements. So here's how they look. This is, again, the first term. A acted on that state to produce the graviton, and here I'm inserting complete set of states. So this is just an S matrix element, a regular S matrix element between some initial two-particle state and the final two-particle state plus a graviton. This is something a little bit different. It looks like a cut of a 5-point amplitude. And the cut includes, of course, an integral over a phase space here. This part here, for example, is P1 prime P2 time P dagger, and this other part here is that. There are two kinds of contributions for each of these terms. One that is connected, your garden variety 5-point amplitude at one loop, for example. And then there's a bit that's disconnected, which we usually discard because it has special momentum configurations. For example, this is a momentum that's being permanently conserved. Now, if we decide to worry about these guys, surely we must worry about their feed down into these cuts. So we have these disconnected kind of cuts and these connected type.
Why is it connected, this second one?
This one?
Yeah.
I'm sorry, which one?
If you cut the second one, if I cut it, don't I get two separate diagrams?
Yeah, no, what I mean by disconnected is one factor is disconnected versus here both factors are connected. Perhaps a poor choice of words.
Okay.
There's a factor that's disconnected here, and here both factors are connected.
Okay.
The cut will always be disconnected.
I understand. Okay.
All right. So before we go on with exactly where the zero energy modes fit in here and so on, I should say that complete calculation along these lines through tree reproduces everything that is known from general relativity perspective. So we are really know the answer is correct. We are really trying to make sense of that answer. All right. So let's take a first crack at the zero energy modes. I didn't tell you where they sit in here. Let's see, can anybody spot a zero energy mode somewhere in here?
A complete set of states.
Yeah, that's true. There are some in here. But again, there are certainly zero energy modes in here that are part of a continuum. Is that they could be part of a continuum, but there's a very glaring zero energy state. Zero energy right here. There is no such thing as an on-shell 1 to 2 S matrix element because there is no phase space for it. At least not for arbitrary energy particles. Right?
It looked like Bremsstrahlung. What's wrong with that?
Bremsstrahlung, you can't have Bremsstrahlung of 3 electrons. You need to be in a field. Here we have no real field, right? This particle sits there, this order, this one doesn't know of that one doesn't know of this one. So it's like having emission of a photon of a 3 electron. That cannot happen unless that photon has 0 energy. So here is the first, our first encounter of a 0 energy mode. And if you go through the song and dance and take this M3 and plug it into the formula I showed you a little earlier about the waveform, you find that there is indeed a constant mode or a 0 energy mode multiplying something that one may recognize. And if you don't recognize, I'll show you what it is in a second. But it's there. And so the question is, what do we do with these? There are 2 options. Ignore them and keep them. There is no third option, really. And one can attempt to justify both of them. One could ignore them because they are special momentum configurations and we never care about these things when we compute S matrices. So why should we start caring all of a sudden now? Well, the flip side of that story is that, well, if we Fourier transform this, we get back to a time-independent metric. So this is something that, in principle, we could live in. And in fact, we do live in. The second one is that if one actually does Fourier transform this, one finds something that one recognizes. It's the asymptotic, is the linearized, is the metric corresponding to 2 Schwarzschild black holes, which is expanded at infinity. So basically, it's linearized Schwarzschild taken twice. Each of these would correspond to 1 Schwarzschild black hole moving with velocity. So this, flip side is it has physical information, corresponds to regular spacetime. And the reason that we are perhaps worried about it is that we are not used to 0 energy modes from a scattering amplitude. All right, so it turns out that these 2 perspectives are connected. And they are connected specifically because at this order, this is static, it's time independent. And it has been shown that indeed there is a BMS transformation with this super translation parameter, which connects the 2. So we're done, basically. If we were done, if everything in the world would be related to these would be time-independent things. However, 0 frequency modes turn out to give also time-dependent things for which it's not immediately obvious how a super translation does, whether a super translation also removes those or it does something else. All right, so let's proceed to an instance where that is the case, that these 0 energy modes actually produce something that is time-dependent. So, anyway, to actually take that into account, there are we need to figure out how to actually include these 0 energy guys into a more complicated scenario, into a more complicated process than these basically disconnected things. There are several options on the market. One is to define creation and annihilation operators at finite distance. This is complicated because the formalism is yet to be fully developed, but at least some people are working. It does provide natural cutoffs, so it's basically like putting the system in a box. So there is no more 0 energy, no literally 0 energy. There is a cutoff of the size of the box. Another approach is to push the outgoing gravitons off shell. And this is a perfectly valid approach if one, and it's actually the preferred approach if one were interested in, for example, constructing the metric at finite distance, not necessarily just the asymptotic one. One would compute a form-factor Fourier transform those. That would be the metric. It also produces a natural regulator because it would be the off-shellness of the outgoing graviton. However, in the process of doing this, small gauge invariance is lost. So Green's functions are no longer not invariant if you replace epsilon by the momentum. So one needs to worry that this kind of things can cause some kind of trouble. And we're going to inspect this a little bit later, especially if I speak fast enough. And we'll see what happens spoiler, nothing fancy, nothing fancy. There is another version of this which injects an auxiliary momentum, but I would as at least for the waveform for the metric it's similar. Small gauge invariant, so we're not going to worry about it. So what we're going to do is to push matter off shell. So this way we will regularize the graviton. The graviton energy, it will no longer be forced to be zero. And at the same time, we're going to preserve small gauge invariance. This is what we're going to, this is how we're going to deal with the zero frequency graviton. So with this in hand, let's proceed to an instance where, to a demonstration that zero frequency gravitons can in fact produce a time-dependent contribution to the waveform. And for that, we only need to look at this cut part of the KMOC formula and pick on one side these disconnected fellows, the ones that correspond to a zero energy graviton. So this is going to have strictly zero energy graviton crossing this cut, and it is strictly zero energy and is not part of a continuum because kinematics of this 3-point forces this guy to be only at omega equals 0. So because it's only at omega equals 0, one cares only about a small piece of this 6-point amplitude, namely its leading term in the soft limit, which looks like that. It's written in terms of the 5-point amplitude. I should have written references on this slide. Anyway, so taking this, multiplying it with this 3-point amplitude, doing the sewing, that is the sum over all the over the two helicity states of the graviton, produces this, where we are still to evaluate one integral, this particular integral, which is where the regularization needs to come in. Because it needs to come in because if you were to try to compute this directly based on what is written here, you will find that depending on how many times you compute it, you're going to get as many answers. So we are going to regularize it, just as I said, by pushing the matter off shell, meaning that we're going to shift P2 in here by some amount, and we are going to not shift it in this form because in this form it was already in here it was already used the on-shell condition, so one needs to shift back to an pushing P2 prime off shell and keeping this entire propagator under the delta function. Anyhow, long story short, once it's computed this way, this is the value of the integral. There's a logarithm that appears, and there's a whole bunch of regularization stuff that comes in. 1 over epsilon from the dimension regulator, and this is from pushing P2 off shell. So all in all, this particular contribution, this particular disconnected cut contribution becomes this. It's proportional to the 3-level amplitude and the coefficient, which is the same t, the same functional expression as the thing that connected the shear 0 with the shear corresponding to 2 Schwarzschild black holes. So putting everything together, so actually before we put anything together, so here, this is literally this piece. It's straight into the waveform. And it has non-trivial frequency dependence on the frequency of the outgoing graviton, M3. This is really the 3-level waveform. So even though everything here is supported by omega equals 0 gravitons, in fact, it has non-trivial frequency dependence there for non-trivial time. So one could, at this order, one could use the wonderful identity 1 plus x equals e to the x. And notice that this indeed looks like wants to exponentiate. If there is an M3 at 3 level, this looks like it wants to exponentiate and it wants to be absorbed into as a shift, as an angular dependent shift of the retarded time. So that indicates that it should have something to do with super translations. So having said all this, the question is, what about beyond this one loop example that I said, where at higher loops, of course, we can't use this identity anymore. One has to make sure that all the higher order terms come with the requisite 1 over n factorial and so on and so forth. So this concludes that leading order and next to leading order example of the relevance of the zero frequency modes. Are there any questions before I show you some more things?
Can you remind us the basic physical picture again, please, in the black hole context? If I have two black holes colliding and I'm observing the gravitational wave, where should I place this picture in this graph? Yeah.
Okay,
So where's my black hole? Where's my graviton?
So the black holes that are being scattered are P1 and P2.
Good.
The
And that
final
blob
state-
represents what? That one?
The blob. Let me tell you first the final state. And
All right.
so the final state is the one that that crosses this the dashed line. So the dashed line is the
I
final.
see a lot of lines there. I see a wiggly line, straight line. So what is final state?
Final state contains one outgoing graviton,
Yes.
and then it contains the particles that come in. And this is another graviton, but that graviton is integrated over.
Uh-huh.
So going back a few slides,
Uh-huh.
yeah. So that picture that this is the waveform, and this whole thing corresponds to two particles going in, two particles and the graviton going out. The last picture that we were discussing is one term in this second term here. And this A is what creates the graviton in the final state. And then the other lines that cross that cut are the evolution of the incoming states, plus whatever else we insert as a complete set of states and we integrate over.
If you go back to the diagram again, please. Yeah. So the loop you are talking about is
The loop here,
that.
maybe I should say that, maybe I should draw this. Yeah. So right. The reason the left and the right of the dashed line are not the same is because of the perturbative expansion. Nominally, it should be this way. This is the entire answer. And in here, we include a complete set of states. Okay. So this A here is the guy that is the A that creates this outgoing graviton. And everything else is the evolution of the initial state. And this X may contain itself gravitons, but they are integrated over because they are exchanged between the two sides of this experiment. Does that make it clearer?
Yeah. Well, the outgoing single graviton that comes to my detector is the one up there, right?
The one up there.
Very
And
good.
The frequency dependence that I was discussing here is the frequency of this guy.
Yeah.
The zero energy modes are the ones exchanged between these two. They are part of this complete set of states here.
You still haven't told me the round blob and the ellipse, the other blob.
It's round. The round blob is a 3-point. The contribution is part of this S matrix. Is the part of this S matrix that takes one particle, one matter particle into one matter particle and the zero energy.
Oh, yeah. So there could be a lot of things in the blob. It's just, I see.
This is schematic. This is an entire.
It's supposed to be very small effects when you start considering, loops and stuff.
No, the only suppression comes from powers of G. There is no H bar. So this, the animation that I showed you in the beginning, that was just leading order. At that order, if you compare that to the next to leading order, stripping away powers of G, they are roughly of the same order. The only thing that's different is powers of G. Where G is not particularly small, it's not particularly big. We can't exactly observe scattering waveforms at the moment because of technological issues, but they are
assumed in interpreting the observations made in the gravitational wave observations. the actual leading contribution, presumably they compare with experiment, with observations, right? What is that leading
So
contribution?
at the moment, I think there are at least maybe at least 3 orders that are included in
What orders?
3 orders.
Oh,
Square G cubed G to the 4th in the
trying to interpret the observations.
that's correct.
Remarkable,
For bound systems, these are actually relevant things.
remarkable. Thank you.
All right, so I have very little time left. So this is so to proceed with this calculation at higher orders, one needs to figure out exactly what are the bits that are actually affected by the zero energy mode. And this is done by essentially direct counting and comparison with what I showed you earlier that how an amplitude should scale with the momentum transfer for it to be classical. So I'm going to skip the standard counting on the left because I'm short on time. So we're going to focus straight on those that pick up contributions from the zero energy gravitons. And the intuition is that we saw here that these zero energy gravitons are special and correspond to something that's disconnected. So let's hope that this continues to be true as we go to higher orders. I haven't told you what's the classical scaling of a process that looks like this. So I'm going to leave it free. I'm going to call it X. And but everything else, I did tell you what it is. This is supposed to scale like 1/q squared to some power that depends on the external. This is supposed to scale like 1/q squared, or with loops, it picks up some contribution that depends on the loops. Each line here is a propagator, so it scales like 1/q squared, and this is matter propagator, so they scale like 1/q. And all in all, we need that this object here, we need it to scale like q to the 1 minus L, where L is the number of external guys that comes up. So before we had L equals 1, so we had one matter coming in, one matter going out, and L equals 1 graviton going out. So this says q to the 0, and indeed, if you think of the stress tensor of a massive particle, it knows nothing about q. It's just proportional to p squared, p mu p nu of the incoming matter. So this is consistent with that. Now, the thing that might give you pause is that as you increase the number of gravitons going out, this thing starts misbehaving. The more you lose here, the more gravitons you lose, the bigger this gets. So as you L equals 1, L equals 2 is q to the minus 1, L equals 3. So this doesn't sound like something classical. So what's this all about? What kind of pieces of, so this looks very much like Compton amplitude, by the way, just crossed with all particles in the outgoing space. Let's have a look at the Compton amplitude and see where these kind of terms would be coming from. So there we had L equal, for Compton, we have L equal to 2, so this should scale like q to the minus 1. So who in the Compton amplitude would give us this? So these are the 3 diagrams that contribute to a Compton amplitude. And the third one, I'll ask you to believe that the third one doesn't do anything useful for us. So let's focus on the first one, on the first 2. So we have an polarization tensors for each gravitons and stress tensors for each of the couplings, and propagators, which are these upon use of on-shell conditions. So expanding at small q, we have this, and I'll ask you to focus on the 2 terms that are in red here. And as one takes the epsilon in I epsilon to 0, one encounters the delta function. And to get this, one uses the Sochotsky formula that produces a delta function, that tries the delta function as the difference of 2 rational functions. So clearly, this scales like 1/q. So this is exactly what would fit in here and would give us something. And we usually refer to these things as super classical because they have a scaling with q that is stronger than classical. They also happen to be supported only on special momentum configurations. We can, of course, kill all the classical pieces by crossing the graviton from the initial state to the final state. Then everything that's classical goes away, and the only thing that survives is this one. This is exactly what goes into here. We have one particle coming in, one particle coming out, and any number of gravitons. So repeating this for any number of gravitons, one finds this object that basically everything collapses to a product of 3-point amplitudes, in which the outgoing momenta are Q1 to QL, but the corresponding delta function sets them to 0. So in fact, they are all the same. To proceed, it is convenient to rewrite this in terms of a creation operator acting only on a 2-particle state, or a 1-particle state in this case. So that involves taking this M3, a creation operator, the corresponding delta function that sits in here, integrated over the phase space. In the process of doing this, we, strictly speaking, identified all of these momenta. So we need to put a 1 over n factorial, because we take this and project it onto an n graviton state, we kill this n factorial, because any one of these can pick up the momentum of any one of these gravitons. So with this, we can also resum all of these emissions. And as we resum all of these emissions, we get, because of the factorials, we get an exponential factor. And I'm going to call this quite conspicuously QS. Q suggests it's a charge. S indicates that it's something soft, and it is certainly soft because it is given by 0 energy gravitons. And its expression is this: there's a creation operator and then this M3. It's basically any one of these factors. All right. So what do we get out of this? Well, the first thing that we get out of this is that, well, we have this QS. Let's see what happens if we decide to conjugate the asymptotic graviton field by this QS. Well, we get 2 terms, one in which QS passes through H, which just does nothing, QS goes away, and then a term in which the annihilation operator inside H talks to the creation operator inside QS. And if one does the calculation, one finds exactly this, which happens to also be the linearized Schwarzschild metric corresponding to a Schwarzschild metric moving with momentum P. So, as I was advertising over lunch, we started with Minkowski space and nothing in it. We resummed 0 energy gravitons. Basically, we pulled them out of the S matrix. And then we fished them out. We assigned them to the state this time. And inside this state, if one measures the expectation value of a graviton, one finds the linearized Schwarzschild metric. Exactly as it should be, because if we put 2 particles in the middle of the space, asymptotically, we should see 2, basically the metric of the linearized metric of 2 Schwarzschild black holes. Of course, there is no horizon because of the large R expansion, but anyway, it is that metric.
Where's the separation between them in the formula?
Yeah, it's whether QS goes straight through H or whether it picks up one commutator. The QS is an operator, H is an operator. There is, A with a dagger gives us something, and it gives us.
Well, if I have 2 black holes separated by distance,
So here,
distance between the 2,
so,
when I linearize the solution, where do I see that?
So you don't see the distance between the 2 because they don't talk to each other at this order.
Oh,
You're going to see basically, so what you're going to get is exactly basically this, the sum of the 2.
the full Schwarzschild is beyond hope, right? I mean,
No, the full Schwarzschild, I mean, the full metric in the presence of scattering and so on, that's very complicated.
some arguments when you are saying it.
Just one metric moving, or one black hole moving, or one static black hole boosted, that is certainly within the cards. And in fact, it was, like I said, it was done sometime in the middle of last year by Van Hove and the collaborators. All right, so now we have this QS here. QS by itself doesn't have any other special properties except that it shifts the metric from basically 0 expectation value to this expectation. So by itself, we can't do much with it. However, there is hope that one could upgrade this operator with something else so that it actually starts commuting with the S matrix. Now, where does that hope come from? Well, that hope comes from the fact that there is clearly a relation between this QS and BMS transformations. And on the one hand, and on the other, BMS transformations have been shown to complete BMS transformations have been shown to commute with the S matrix. Therefore, it should be, at least in principle, possible to ask what is this Q, what's the upgrade of this QS that does have correct commutations with the S matrix, namely it does commute. Now, just to step ahead, because again, the time is short, if we had such an operator, let's have a look at what would happen with this final state expectation value. Well, as we pull out the S matrix, this QS, for suitable incoming states, for example, states with no gravitons, one could add for free this extra operator that makes QS commute with the S matrix, call it QH. One could add it for free because it does nothing. Then take this and push it through the S matrix. So instead of worrying about all what the zero energy modes do and so on and so forth, all one had to do is to conjugate the observable with this QH plus QS, and then ignore all the zero energy modes in the S matrix. This is a reasonable prospect to aim for, given that these are not necessarily easy to deal with at higher orders. So let's attempt to construct such a QH. And a little bit of thought, and I'm going to be bold. So I was saying earlier that we pulled out this zero energy modes out of the S matrix, and inside the S matrix there are none of them left. I'm going to be bold and forget that I did that. I'm going to take QS as we construct it and keep the zero energy modes in here, in particular the ones that are attached to matter particles, because those attached elsewhere we didn't remove. So we're going to take the complete S matrix and attempt to see if there is a way to make QS commute with it. So there are two kinds of contributions from this. One in which the creation operator inside QS talks to a graviton that's attached to a matter particle, and one in which it's attached to a graviton. These guys, the first kind of guys, those are the ones that we could in principle ignore if we subtract all the zero energy gravitons attached to matter from the S matrix. This is the S hat that I was having here. The second ones we can't ignore. So let me skip the first guys and focus on the second guys. So I'm sure you recognize this diagram because it looks very much like the one that we discussed at one loop. And again, just as before, just as in that calculation, this red graviton is zero energy because it comes from a QS. So in fact, it's only the soft limit of this complicated amplitude that's relevant. And then basically one is left with an integral that's exactly the same one that we had at one loop, and everything else stays put. So we find that, this is the integral, and it's again the same as before. And one can mimic this contribution by another commutator with the S matrix, one that this time involves the graviton itself. So it looks like this. It's a number operator for the graviton, and the coefficient that's built out is I. And this is how it really looks like. It's the same T the same object that we encountered at one loop, except that now it's summed over all the matter particles because at one loop we had that sum explicitly written out as two particles. In principle, this is true for any number of external. So we are basically done. Even though I rushed through this last bit, we constructed explicitly two. There is a third one that deals with a matter particle. We constructed a Q that commutes with the S matrix, and then we can play with it. And these are the expressions of those Q of the pieces that go into this charge. So let's see, what are the consequences on the final state observables? Well, like I said, all we have to do is, again, start with an initial state that doesn't have gravitons. We have this QS that we pulled out. We can add the QH for free, right? So QH, especially the 0 one, the one corresponding to gravitons, we can add it for free for an initial state with no gravitons because it acts when it is 0. There are no gravitons here. Then we have a combination that commutes with S. We push it through, and then this is what it is. So let's compute this for let's compute this conjugation for the graviton measurement function. So there are now two contributions. One is the Schwarzschild part that we had before, coming from the creation operator in H talking to QS. We have now we have a second factor that comes from the creation operator in here talking to the number operator inside QH. And that basically produces just a factor of this stuff, curly QH0, which is that K0 times T. So this is this factor here. So this actually realizes what I was saying earlier. At one loop, we had 1 plus x equals e to the x. Here we have the full e to the x that appeared. It's the exponentiation of that one loop calculation. And again, taking this and shoving it in here allows us to, at least in principle, absorb this into the retarded time by a shift. So that's the BMS super translation that comes out of this scattering amplitude calculation. All right, any questions?
Well, if it is BMS super translation, doesn't it mean that it can be gauged away? It's not observable, physical observable? The contribution of zero energy. I mean, why is it not a pure gauge effect? BMS super translation is residual symmetry, I suppose. Oh, it's global symmetry. I'm sorry. So I can get rid of it. Sorry. Is that correct? My interpretation.
I mean, it depends. So
if it is a local residual symmetry, I have the right to use it to gauge away unobservables, right? I mean,
so it depends, right? So it depends in the following. This is what I was saying earlier, that if we had two detectors that are sufficiently far away, then we can tell them apart, right? So when scattering happens at one value of the time, right? T equals 0. So one could, if one had a single detector, one can always shift the time to pick that T equals 0. Now, if one has another detector, surely we're going to fix the time once at one angle. If one has another detector elsewhere at a different angle configuration, then one has no more freedom because the origin of time was fixed once.
oh, I see.
Now, is that a viable, an experimentally viable?
Well, that's not is it in as a matter of principle? I think you've explained that.
As a matter of principle,
The physical effect. Okay.
and basically all of this has to do with the fact that even though I didn't write these arguments as theta and phi, these are actually angle dependent. They depend on the angle on the celestials. So another important observable in general relativity and in general is the angular momentum. In this case, the angular momentum that's emitted that's taken away by the gravitational wave emitted during the scattering process. So this is how the angular momentum looks like. I mean, I should say that the fact that the angular momentum is dependent on the BMS frame has been known since the beginning of time, basically. This formula due originally to Peters and Thorne and probably others make it dependent on the undifferentiated shear, this DC, undifferentiated with respect to the time. So clearly this makes it dependent on the BMS frame. And in fact, there's a curious situation that had developed over the last few years. So the puzzle started with the observation that energy is first lost at order g cubed, but angular momentum appears to be first lost at order g squared. And where does that come from? It turns out that this order g squared depends exactly on the BMS frame. In some frames it exists, in some others it doesn't. When it doesn't, it's called the canonical frame. The other one is the intrinsic frame. In any case, direct calculations using amplitudes methods demonstrate that this order G square is in fact accurate and contributes to, for example, the scattering angle of the two black holes. And sometime afterwards, it was this order G square was explicitly calculated using amplitudes methods, and indeed it turns out to be generated by zero frequency modes. And Veneziano and Wilkowicki also understood its relation to BMS transformations. And this is given by this T, the same T that has appeared everywhere earlier. All right, so in our language, what does this mean? Well, L, the angular momentum operator, is a bilinear in creation and annihilation operator for the gravitational field. So we get to play exactly the same game. Start with an initial state that has no gravity. Pull out QS. Expand it to include also QH for free. And then insert identity in here. We should have the same color. Therefore, everything is written in terms of the conjugation of creation and annihilation operators with this QS plus QH0. So this gives two terms, one that's called alpha, that's a constant, it's a shift that comes from QS, and the phase that comes from QH. The phase is with exactly the same T. It turns out, so all one has to do is take this, plug it in there, and integrate. It turns out that the terms with two alphas integrate to zero based on symmetry reasons. Terms with a single alpha, they start out their lives at order G cubed. 1 power of square root of G coming from the 3-point amplitude in alpha, and 3 powers of square root of G coming from the other expectation value here, this from the expectation value of A. And this reproduces the order G square angular momentum loss that I was mentioning earlier, and also the direct evaluation by Manohar and company. And then there's a third bit, terms with no alphas. This one also splits in two pieces. One might call the canonical bit and the hard bit. The canonical bit comes from the terms in which these derivatives act straight on A. They don't act on this T factor. And that's basically the, if you wish, the standard one, the bit that's independent of the BMS frame. And then the hard part looks like this. It's manifestly proportional to derivatives of this T. And it starts out its life at order G to the 4th, 1 power of G from T, and then 3 powers of G from the expectation values. And this is also related to a memory effect, except that it is the nonlinear memory effect this time. And this has been mentioned that it has been mentioned earlier that the nonlinear memory effect starts appearing at order G to the 4th. So I am out of time by 5 minutes. So I should stop. The only thing that I wanted to add here is the following. One can now that we have this QS and so now that we have this Q, which is QS plus QH, and it looks like it wants to have something to do with BMS transformations. It's reasonable to wonder what happens if one computes its expectation value in the final state. So that should give us, and perhaps subtract its expectation value in the initial state. This should give the change in the in this charge between the initial and the final state. In a perfect world, this should match the change in the supertranslation charge between the initial and final state, which takes this expression. So it turns out that this is what one gets with a little bit of there's a little bit of a calculation that goes into this. And this F here, this is defined to be what? This F is defined to be basically the asymptotic metric up to some numerical factors. So this is what comes out from Amplitude's perspective for this delta Q. And this is what comes out for this delta Q classical if one uses the formula for the Bondi mass loss in terms of this normalization of the shear. By inspection, they look very much alike. So quite unlike the usual case, this happens to be a perfect world, to actually agree. There are some limitations to this comparison. One, we assumed that there are no gravitons in the initial state. And two, we assumed we did not include the change due to the matter in this super translation charge. If one were to introduce them, they should add up to 0, but we have not quite checked. So this brings me to the end of my talk. I'm sorry for going over time. I will not read what I described. I'm going to leave you with blue stuff, which are questions for some future. Is it possible? So this is, I was debating my title in the beginning, should the plural be there or should it not? We really discussed today one super translation, one given by this particular T. Is it possible? Is it possible to include in this format more general ones? And
How many are there?
infinite. I mean, it's T can be in general. One can translate at the time by any function of the angles. This was a very special. This was a very special shift. But in principle, one could wonder. Also, is it possible to include super rotations in a similar framework? One can also wonder what other observables depend on the BMS frame. We discussed the waveform and the angular momentum. The first one is clearly dependent because it's the metric itself, and that's what super translations do, change it. The other one has been known for a while to dependent. We basically understood how that changes, how that dependence comes about in our framework. But are there others? For example, is the scattering angle of two black holes supposed to depend on the BMS frame? I don't know. What about other theories? Is there any relation between super translations and properties of Yang-Mills via double copy? What about remnants of BMS at finite distance? There is no symmetry at finite distance because things change, but metric spacetimes are affected by BMS transformations at infinity. How does that affect anything from an amplitudes point of view? In any case, I believe these are interesting questions, and I think we should expect further new results and perspectives as far as symmetries in gravitational theories are concerned. Thank you very much.
In observations, the waveform is being observed, right? But not angular momentum, right? Correct. That's probably very small.
In principle, given a waveform, one can construct the angular momentum. Right, so I skipped over that slide because I was running out of time. But here, what is being observed ultimately is the shear. So the angular momentum, once one had the shear, one could in principle plug it in here. There is one little, so it involves an integration over the celestial sphere. If we were to observe anything, we observe C, we observe it at 1 theta and 1 phi. We can't do the integral.
So waveform is the solid under control.
The waveform is what LIGO measures. Right.
One last question is there any probabilistically and statistically any chance in the universe that there are 3 black holes colliding or interacting closely with each other, let's say? Is there a chance? Have people ever even uttered the possibility?
There's some literature about this. Yeah.
Really? Already? 3?
Well, I mean, yeah.
So what do you compute then? Again, a single graviton escaping the...
So most of... There has been some analysis. There is some literature about this, both from observational point of view, astrophysical point of view. They certainly, I mean, strictly speaking, none of this actually has to do with black hole. Bodies don't really have to be black holes. Neutron stars are just as good. You know.
But what are the chances 3 neutron stars get close to each other and scatter? I mean,
There's
no observation, right?
It's not ready for me to answer. It's from the astrophysical.
Your guess is that there will be no known observation. Is there, as far as you know?
No available observations, at least not with gravitational waves. But anyway.
Okay. And even optically, I mean,
yeah, I mean,
probably it's hard to get by this, right? Okay.
Like I said, I'm the wrong person to answer this question, but
Astronomers, so I will go and check on that.
it's them who should answer that.
Okay.
There's certainly literature about this.
Theoretical.
Theoretical, three-body systems have been discussed specifically, especially the hierarchical ones. Say two bodies are sort of bound and then there's something off of that.
Gravity, everything studied.
And, we encounter this all the time, right? There are comets passing by. So, the solar system is bound and then comet passes by. That's the third problem. Yeah. But yeah, so
People do Newton mechanics.
in that context, that's fair. In that context, Newtonian mechanics is perfectly accurate. There are, globular clusters, just to throw out some words. But yeah, there are dense regions that, dense by some definition of dense. And from a theoretical point of view, people have constructed things like three-body potentials that would integrate out gravity and reduce three-body motion to basically potential problem, just with a very complicated potential.
Thank you.
One could, in principle, repeat everything I said to such a scenario.
Thank you, speaker.
Thank you. These are not walk in the park calculations.